Hello, dear participants. Welcome on the Bioinformatics sessions. My name is Marcin Kosinski. I'm the leader of the foundation, and I have a pleasure to host this session today. We have 5 great speakers. First, we will have a speech by Agnieszka Borsuk-de-Moor about non-stationary pharmacokinetics of caspofungin in ECPU patients. So good luck, Agnieszka, and wish you all the best.
Thank you, Marcin. Just a few words about me. I'm Agnieszka Borsuk-de-Moor. I am a PhD student at the Department of Bioinformatics and Pharmacodynamics at Medical University of Gdańsk, and I would like to present some results from a study on caspofungin in intensive care unit patients. So maybe a few words about pharmacokinetics. What is it? Pharmacokinetics describes the concentration time relationship of a drug in the body after the administration of a dose. It can be described by ADME acronym, which stands for absorption, metabolism, distribution, and excretion. A few words about caspofungin. What is it? It is an antifungal drug. First of the echinocandin group of drugs, was the first one that was approved of this group. And what is special about echinocandins is that they selectively target fungal cell wall by blocking glucan synthase complex. So since mammalian cells don't have a cell wall, the mammalian cells are not affected by this drug, which leads to less adverse events due to administration of caspofungin. And caspofungin is indicated for invasive candidiasis and invasive aspergillosis, which are a problem in treating critically ill patients. Invasive candidiasis is associated with mortality rate even up to 53%. And the longer you wait with the treatment, the less chance the patient has to survive, as you can see on this plot. Intensive care unit patients are at great risk of invasive candidiasis due to all the procedures that they undergo. They have a lot of catheters, they undergo very invasive treatments, and also they have altered physiology. So on one side, they are associated with a lot of risk factors, and also due to this different physiology, standard drug dosing might not be adequate. Here you can see a picture of extracorporeal membrane oxygenation. It's like a big machine, and a lot can change in the body of a patient if he's undergoing such a treatment. So the aim of the study was to investigate the pharmacokinetics of caspofungin in a special group of patients, in the intensive care unit patients. Then we wanted to explore how patient characteristics and vital parameters of the patients and the treatments they undergo, how these factors affect pharmacokinetics in this group of patients, and lastly, to assess the exposure to the drug. It was an observational clinical study with 30 adult critically ill patients. There was a subgroup of 3 patients with liver failure. All of these patients had severe sepsis, and they had a high risk of fungal infection. That's why they were administered caspofungin. It was given as an empirical therapy once daily. The loading dose was 70 milligrams, and then maintenance dose 50 milligrams. The patients with liver failure had reduced dose. We recorded some of basic demographic covariates such as sex, age, weight, height. Also, some clinical covariates such as scores that describe the severity of the illness, the concentration of procalcitonin, dialysis, ultrafiltration rate, and also the severe treatments they were undergoing, so whether they needed the extracorporeal membrane oxygenation and continuous renal replacement therapy. Blood samples were collected in an organized manner, up to 6 samples after each dose, and the patients were monitored for 3 consecutive days. As you can see on this plot of raw PK data, there are indeed 3 consecutive doses monitored. The data are nicely organized, and since for each patient we had data after 3 subsequent doses, we could also assess the inter-occasion variability in concentration time relationship. So the structural model of pharmacokinetics was described by a 2-compartment model where parametrization was through volumes of distribution and intercompartmental clearances, which are more physiological way of parameterizing such models. Was intercompartmental clearance and elimination clearance. Clearance is the most important parameter here because it describes how quickly the drug is eliminated from the body. The equilibrium can be described here by differential equations. So over this structural model, we build a population model, assuming inter-individual variability in population PK parameters. We assumed a log normal distribution. We also incorporated inter-occasion variability using the kappa random variables, and we assumed that residual variability had a proportional manner. So we used nonlinear mixed effect models to estimate model parameters. The first model that was developed included inter-individual and inter-occasion variability, and as you can see at this goodness of fit plots, the fit was pretty good, but what raised attention was a certain drift in conditional weighted residuals versus time. It doesn't look that significant, but I was curious about it, so I decided to investigate it further. And I saw that there was a drift in time in the kappa variables describing inter-occasion variability. So it was changing with time. I could see that clearance was rising as well as volume of distribution. I tried to search the relationship between for this phenomenon. I tried to explain it with covariates that were registered in the study, but there was no relationship. So this phenomenon can be seen in individual plots for each patient. For example, patient number 7, you can see that indeed the concentrations with time, they're actually going down, while since we are giving a loading dose, the concentrations here should be similar. Like we want to have a steady state, while you can see it's not achieved here. So I also tested non-linearity in clearance that could be due to activation of liver enzymes, but it didn't improve the model fit. So I decided on an empirical model that included 3 separate values of clearance and volume of distribution for each occasion. And here is the goodness of fit plot for this model. So I removed the inter-occasion variability and instead used 3 separate clearance values for each occasion. And this drift that was seen here is not there anymore. So, and the model was vastly improved. And then for this model, I still searched more covariates that could explain inter-individual variability, but sadly I didn't find anything, which is surprising since the patients were critically ill and you would expect some relationship. maybe not with body weight or age, but at least with procalcitonin levels or SOFA score, dialysis, ultrafiltration. There are some hints here, but as I tested it formally in the model, it did not improve model fit. Since the caspofungin is 97% bound to proteins, there should be a relationship with albumin, but it was not found. What's interesting is that I didn't find any differences between patients who were undergoing the ECMO therapy and continuous renal replacement therapy, but there is there could be something happening for the patients with liver failure, but there are only 3 patients, so this is rather a start for further studies rather than any conclusive study. Here is the visual predictive check of the final model. As you can see, the simulated data are in good agreement with the observed data. So we stayed with this model as a final model. Now a few words about the results and the values of these 2 parameters that were changing with time. So as you can see, clearance is changing day to day, and it's a big difference, which I will comment further. There is a slight shift in volume of central compartment distribution. A few words maybe about the individual variability that was observed. With clearance and volume of central compartment, it is around 25-30%, which is on the level of like a normal variability in PK parameters in any population. There is a little bit more for the volume of peripheral compartment. But to find a covariate that would explain inter-individual variability, it would be difficult to find something that would be clinically relevant, because you need at least 20% decrease in variability for the covariate to be really clinically relevant to adjust dosing. And since these values are not that high, that wouldn't be even possible to include in the clinical setting. I'm going to talk a bit about the clearance because it's the key parameter that determines drug exposure, since the exposure expressed as area under the curve is determined by the dose that the clinician can adjust, and the clearance that is specific for the patient. So the estimated clearances for the first, second, and third occasion were like this. So the first one is well within the values that were reported in the literature. The second one is within the highest previously reported values, while the third one is almost double of the first one and much higher than the literature values, which will have some consequences. If we make a simulation with a maintenance dose of 50 milligrams, the area under the curve based on these clearance values would be around 90, around 70, and around 50. And now let's analyze it in context of the minimal value required for drug efficacy, which is considered to be around 100. So you can see that in any case, none of the cases, this target is achieved. It's all below, and for the third clearance is much below the target. And between the doses, we achieve decrease in exposure by 24 and 44%. So this should raise awareness that there's something going on with caspofungin and its clearance, and that it should be further investigated because such values would actually be good to change actually the dosing of caspofungin if it's true. So to conclude, the pharmacokinetics of caspofungin was non-stationary in our study. Of course, the model was strictly empirical, and this should be further investigated. And the change in parameters was not explained by any of the recorded covariates. This decrease in exposure was clinically relevant since it was more than 20%. It could be characteristic for the studied group of patients, but it doesn't have to be, so it should be further investigated. And since the steady state was clearly not achieved because the concentrations were shifting, and the concentrations seem to be suboptimal with the dosing that was used in this study, we would really suggest additional studies to investigate the PK of caspofungin. And that's it. Thank you for your attention.
Okay, thank you, Agnieszka. Just right in time, exactly 15 minutes. So thank you. If you could stop sharing your screen, we will be able to start with the second speaker. If you have any other questions for Agnieszka, you can follow up on chat or on Slack. Yes, so the next speaker will be Lubomir Stepanek. Lubomir, are you with us? Oh, there you are. Excellent.
So may I share my screen?
Yeah, you should be able to share the screen.
I'm going to do it.
And that's going to be a machine learning approach to survival time event modeling and predicting with R. Good luck, Lubomir. You've got 15 minutes and enjoy.
Okay, so good morning, ladies and gentlemen. Hello to everyone. I've got this amazing opportunity to tell something about our research. My name is Lubomir Stepanek, and I just come from the first faculty of medicine, Charles University in Prague, and from the faculty of informatics and statistics, University of Economics in Prague. And our team and me is interested in survival analysis and its applications. This is just a topic I'm going to talk about. And it's a big pleasure for me to say this is just a joint work with Filip Habarta, Ivana Mala, and Luboš Marek. So let's have a look at the intended outline of my talk. So I will start with a quick introduction where I'm going to introduce some motivation and some basic terms about survival predicting, traditionally based on a Cox proportional hazard model. Then I will continue with a description of both the data and the methodology we have to use to overcome some limitations, statistical limitations of the Cox regression. The methods we employed are usually based on machine learning algorithms. After that, I will follow with some results we have got so far and which could describe the performance of the alternative method we have proposed. And finally, I will try to point out some key findings. So the predictions apply survival data explaining whether an event of interest is even likely going to happen to a given individual. It is usually defined by independent variables. And if so, when exactly the individual could expect the event. It's an important task and commonly solved by several models. Usually, the Cox proportional hazard model and many other variants of this model, which are derived from the Cox original model, are used to handle this task. But I would say that these models are limited by statistical assumptions, mostly by the assumption that the ratios of chances of being in risk for individuals should be equal for all of them, for all individuals across all the time points. So in this study, we didn't follow the logic of the Cox modeling. So we didn't estimate the event's hazard function that is defined usually as a probability that a subject experiences the event of interest in a small time interval, given that the individual survived up to the beginning of this interval. But we rather prefer to make direct predictions by decomposition of the two-dimensional dependent time event variable, depicting the event occurrence and time to the event into these two independent components, which overcomes the statistical limitations of the original Cox model. So the first part of the variable stands for the event occurrence and is considered as a classification task. The second part, this dependent variable, is for the time to event estimation and is assumed to be a regression task. Here we can see an example of a survival plot, curve plotted in a survival plot. The target variable is survival analysis. Is two-dimensional, covering both the time of the event and whether the event or the censoring has been occurred. Intuitively, such a variable is just being plotted in two-dimensional chart. where usually a number of the subjects not experiencing the event of interest to a number of all subjects is plotted on a vertical axis at a given time point, while the horizontal axis stands for the time until the event of interest or until the censoring. Since the target variable is two-dimensional, it can be decomposed into two independent components, and as I told you before. So now we are moving to data we used in this study. So data we used describe various variables about more than 40 patients having stomach cancer. The patients attended one of the Prague-based Department of Surgery in years 2013 to 2017, and they underwent their appropriate treatment. Of course, they were fully informed about all the aspects of, of the treatment and the study. The dataset contains more than 30 variables used to predict whether the event of our interest, it means death of a patient due to the stomach carcinoma, did occur and when. And to build the predictive models, so it includes both numerical and categorical variables such as age, number, positive lymph nodes, blood levels of various cancer markers, time to surgery, time to recurrence, time to death, and for example, sex, GNM staging, various clinical scores, cigarette smoking, alcohol abuse, second type of diagnosis, and so on, so cancer recurrence or death occurrence. Well, now we are moving to the original Cox proportional hazard model. So the Cox proportional hazard model is commonly used to model a relation between the hazard function of the event of interest, which is defined, as I already told you, as a probability that the subject experiences the event of interest in a small time interval, given that the interval survived after the beginning of this interval. And the relation is between other explanatory variables. It's also used to predict occurrence and time of the event for a given individual. Cox proposed to estimate the hazard function depending on explanatory variables in the form which is described by the formula you can see. So that the following formula, we need to estimate the linear coefficients for appropriate exploratory variables, which can be done by a partial likelihood, for example. Okay, once we estimated the coefficients and built the Cox model, we had to predict for each interval in the data set if they are going to experience the event of interest given the model and given the coefficients. It was done by calculation of the mean time, average time to event expectation using the estimated hazard functions, as you can see in the formula. And then whenever the mean time to event expectation for an interval was lower than the length of observation period, the interval was assumed to experience the event of interest. It means, in our case, to experience death due to the stomach carcinoma. Otherwise, the interval was supposed to be only censored without any death. Now let's move to the assumptions and limitations of the Cox model. If we rewrite the formula for the Cox model, such that we take a ratio of two left-hand sides and two right-hand sides for two different intervals marked by subscripts 1 and 2, we can see the hazard ratios for any two individuals is forced to be constant. So in other words, the ratios of hazards for any two subjects should be constant across all time points. This is why the Cox model is sometimes called proportional hazard. And however, this assumption is often not met in survival analysis for some real data. And I'm going to illustrate this on the next two slides. So here in this plot, we can see two survival curves, and also we see that the curves cross each other. Definitely, their hazard couldn't be proportional constant across all time modes, since the hazard function for the solid line is larger than the proportion of the dashed line, than the hazard of the dashed line till the crossing point, but is switched vice versa after the crossing point. And similarly here, because the dashed line drops to 0 while the solid line still levels off, although their hazard proportion changed from a non-zero value to 0 after dropping of the dashed line to 0. So now we are moving towards the machine learning based predictions. So firstly, we decompose the time event response variable into two parts. The first part describes the binary occurrence of the event of interest, and the second part estimates the time to the event of interest. While the first part of the variable was treated as a classification task, the second part was treated rather as a regression one. We used machine learning algorithms to build models predicting the target values. And in case of the first part, which was treated as a classification task, we used machine learning classification task algorithms such as logistic regression, naive-bayes classifier, classification trees, support vector machines, and neural networks. And in case of the second part, which was treated as a regression task, we used machine learning regression algorithms such as linear regression, regression trees, and neural networks. So the linear regression was performed to estimate the time to the event. For a given interval, we used the default stats package, R package for this, and the linear regressions were estimated using the minimal sum squares for residuals. That's not rocket science, definitely. Similarly, the logistic regression predicted whether the event of interest will occur or not, and was learned by GLM function also from the stats R package. So this is like fundamental stuff in R. Nearby classifier also predicted the occurrence of the event for a given individual, assuming that the proportions of the events of interest are constant in the dataset. Definitely they are. The naive-based classifier simply picked the occurrence based on a maximum a posteriori principle. It was implemented using the E1071 package, and also regression classifier trees, which were implemented using RPAR package, helped to predict both the occurrence and the time to event of the interest. The trees divide all the universe of all exploratory variables into some disjunctive orthogonal subspaces in accordance to likely distributions of target classes in this universe. And by this division, rules using the exploratory variables and their some of the values, either for classification or regression estimates, are created in this base process. So Supervector machines are native classifiers splitting the space of all exploratory variables into two subspaces by a hyperplane and by maximizing the margins between the hyperplanes and the closest points of the both subspaces. So this approach was implemented by package E1071 together with the application of the kernel trick, artificially increasing the dimensionality of all the variables spaces, and also it was used to predict the event occurrence. And finally, the neural networks, they were implemented by a neural net R package. We set this with this sigmoid activating function with 3 hidden layers, and by professional learning, it was performed both for prediction of the event occurrence and for time to event estimation. Well, now we are just moving to some results we have got so far. So the confusion matrices for all the algorithms used as classifiers to predict whether the event of interest, death due to stomach carcinoma, did occur or did not. And they are displayed here on this slide and the next one. So the best predict accuracy as a proportion of a confusion matrix trace to confusion matrix sum was returned by the classification trees. It is about 0.78. Together with support vector machines, it was about 0.68, and neural networks was about 0.70. And furthermore, the predictive accuracies are similar to the Cox regression's predictive accuracy, which was about 0.75. And this is just could be just a way in this way that the traditional approach of the events occurrence predicted by the Cox regression could be replaced by usage of the classification trees, or eventually by usage of support vector machines or neural networks, respectively. And in case of classification trees, the predictive accuracy was even a bit better than D1 for the original Cox model. So one would expect that for larger samples, the classification trees may work even better than the Cox regression, Cox model. Supposing the fact that the classification trees are not unlike the Cox predicting model, limited by so strict statistical assumptions. Well, the predictions of the times to event, which were made using both the Cox model and the machine learning algorithms, they were usually compared using a root mean square error, which is a commonly used metric for regression tasks. So the lower the root mean square error is, the closer the real values are to the estimated ones. And we can see that we got the lowest root mean square error for the neural networks. What is more, also, the root mean square error for the neural networks is similar to D1 returned by the Cox predictions, so that the neural networks predicting time values, the time event variable, seems that could be used instead of the Cox model predictions. Well, to conclude this up, I would say that the predictions of time to the event of interest is a crucial task in survey analysis, enabling to schedule, for example, just in time and important steps to reduce effects of the, for example, inevitable events. And while the time to event predictions are usually made using Cox proportional hazard models, we showed that the decomposition of the variable into two parts, it means event occurrence and time to event part, and they are independent predictions using both the classification and regression algorithms of supervised machine learning. It seems to be a valid alternative to the Cox model. And what is more, the proposed approach based on the decomposition and on the machine learning algorithms deployment is not limited by such strict statistical assumptions, and thus we could expect better performance for larger samples. Yeah. So the preliminary analysis applied on stomach cancer data indicated that the combination of classification trees for prediction of the event of interest occurrence and neural networks with backpropagation for time to event estimation, it seems to be of even equal or even better predictive performance than the Cox model. It's just a preliminary study, but it was just the results we got. Okay, so thank you for attention. If you have any question, I can try to answer in the chat. So yeah, that's it, guys.
Okay, thank you, Lubomir. Just in time, exactly precisely 15 minutes. So I don't think we have time for any questions, but if anything pops on the chat, you are more than welcome to go there and answer. There is also a Slack where we can all follow up. And now I would like to go with another presenter. Lubomir, if you could stop sharing your screen, we would have Katarzyna Sidorczuk right now. Katarzyna will present AmpGram in search of antimicrobial peptides in R. Yeah, Katarzyna, if you could also turn on your video, that would be great.
Okay,
and
so
good luck.
be able to see me and my presentation. So, hi everyone, my name is Katarzyna Sidorczuk. I'm a PhD student at the University of Wrocław, and today I would like to present AmpGram, a software for prediction of antimicrobial peptides. Let's start with a short introduction into the biological aspect of this project. We work with peptides, molecules that are composed of amino acids. There are 20 standard amino acids which are encoded by letters. And the important thing is that amino acids differ in their physicochemical properties. They may be, for example, negatively or positively charged, polar or hydrophobic. And we are especially interested in antimicrobial peptides. They are short and widespread in all living organisms. AMPs are characterized by the presence of many positively charged or hydrophobic residues, and therefore they are able to interact with negatively charged bacterial membranes. Actually, there are a few models describing how these interactions may occur, but the most important thing is that they cause membrane permeabilization. And you should also keep in mind that AMPs may be active against bacteria, viruses, fungi, parasites, or even cancer cells. Therefore, they are considered as an important alternative to traditional antibiotics, especially considering the current drastic loss of antibiotic effectiveness. There are many programs that predict AMPs. Some of them are also accessible as web servers, for example, Adam, AmpScanner, or CampR3. But most available software exhibits strong length dependence. And the problem with prediction of these longer peptides is associated with the fact that AMPs are mostly short peptides. And as you can see on this graph, the difference in amino acid composition of AMP and non-AMP peptides are decreasing with their length. And the reason for this similar distribution in longer peptides is that only a short fragment, for example, 20 amino acids of a peptide, may exhibit antimicrobial properties. And essentially, this signal is lost within the rest of the peptide that has no antimicrobial properties. And our goal was to create a software that would identify those typical short AMPs, but also fragments with AMP properties within longer peptides. So to create a positive data set, we used over 12,000 sequences from the DBAMP database. We removed peptides containing non-standard amino acids, and then we used a CD hit program to remove those with sequence identity over 90%. After that, we were left with only 2,463 peptides. And for construction of the negative data set, we downloaded over 500,000 sequences from the UniProt database. We ensured that they were experimentally validated to not display any of the antimicrobial properties and also not possess mitochondrial plastid transit peptides, because those peptides are hypothesized to evolve from AMPs. So the downloaded sequences were concatenated into a single string, from which we cut off blocks equal in length to all the AMPs. And next, within those blocks, we cut off sequences corresponding in length to AMPs, and we randomly selected one sequence corresponding to one AMP for the negative data set. This way, we ensured that length distribution and number of sequences were the same in both datasets. Then all sequences were divided into 5 equally sized groups of sequence length, and we selected 1/10 of sequences from each group to create the benchmark dataset, and the remaining sequences were used for training and testing. Next, we divided all the sequences into overlapping 10-mers, that is subsequences of length 10. And the important assumption that we made here is that we consider all 10-mers from the positive dataset as AMPs, and all from the negative dataset as non-AMPs. Then we use those 10-mers to extract n-grams of length from 1 to 3, and with different gap lengths. And at the end, n-gram counts were binarized, meaning 1 if n-gram was present and 0 otherwise. Next, we performed 5-fold cross-validation using different length groups of peptides, and we found that the best results were obtained when using peptides of length from 11 to 26. For model training, we used over 13,000 of informative n-grams that were selected using quick permutation test from the Biogram package. We grew a random forest model with 2,000 of trees and different tri-parameter using the Ranger package. And this way we obtained model that classifies each 10-mer as a potential AMP or non-AMP. Next, to scale those predictions to the whole peptides, we calculated 14 statistics from 10-mer predictions for each peptide. For example, a fraction of mers predicted as positive, length of a peptide, median value of prediction, and so on. And those statistics were used to train the second random forest model, also friendly package, and this is the final architecture of our algorithm. So how does it work? We take a peptide, divide it into 10 mers, and then the first model is used to yield predictions for each 10 mer. Then we summarize those results by calculation of statistics that are used by the second model to predict if a given peptide is a potential AMP or non-AMP. So to evaluate our software performance, we benchmarked AmpGram with other AMP predictors on our benchmark dataset. And here you can see results for all length groups and for the longest peptides. And you can see here that for all lengths, the best performance is achieved by AmpScanner. However, when you look at the group of the longest peptides, you can see that AmpGram is almost as good as AmpScanner, but what I would like to point out is that this dataset was really small, and it was biased as the other algorithms could use those peptides for learning. That's why we also benchmarked AmpGram using the external datasets. They were published by Gaber and Noble, and the performance of AmpGram on the first APD dataset is comparable with that of AmpScanner. But what's important is that AmpScanner was specifically trained on those sequences from the APD database. To ensure that we compare ourselves on an unbiased dataset, we modified the second one, the AMPD dataset, by removing all sequences that were used to train AmpGram or AmpScanner. And on this unbiased dataset, you can see that AmpGram outperforms all other algorithms. Next, to see if AmpGram is able to predict regions with AMP activity, we tested it on proteins for which such regions were experimentally validated. And here is an example for lactoferrin. On the x-axis, you can see the amino acid position within the sequence, and on the y-axis are prediction values for given 10 mol. The experiments, it was shown in the experiments that 3 regions of lactoferrin possess antimicrobial properties, and they are marked by those red boxes. And you can see that in all 3 cases there is an accumulation of MERS predicted as AMPs. And you can also see that AmpGram detected even more potential regions that could possess antimicrobial properties. I would also like to mention how we managed to submit AmpGram to CRAN, because our first model was really large, and even when saving as an R data file with the highest compression, it was still 14 megabytes. And the size limit for files uploaded to CRAN is only 5 megabytes. The solution was to store our data, that is both informative ngrams and 2 models, in a separate package, AmpGram model, which is available on GitHub. And basically, AmpGram was submitted to CRAN with the note that it requires installation of an externally stored package for proper functioning. Okay, so AmpGram is also available as a web server. The R package is meant mostly for larger analysis, for example, for proteome screening. And if you are interested in getting some more information, you can check out our paper or see the code used for analysis. The whole workflow is implemented using Drake and Renf packages to ensure its reproducibility. Okay, and I would like to thank all of my colleagues that were working with me on AmpGram. And of course, thank you all for your attention.
Okay, thank you, Katarzyna. We have 1 minute, so if you'd like, we could have one quick question, but actually we started the session later, so I think we're good.
If there are any questions, I can answer them on Slack later.
Yeah, makes sense. Okay, so if you could stop the screen, we could have another speaker, which is Jarosław Hilimoniuk, who's gonna present count data analysis with countfitteR. Yep. Yeah, if you could try to share the screen again. Okay, nice and clear. If you could also turn on your video.
Yeah.
Okay, go for it.
Yeah, so hi everyone. I'm Jarek Hilmoń from the Department of Bioinformatics and Genomics from the University of Wrocław, Faculty of Biotechnology. And today I want to present you one of our packages, countfitteR, which was designed mainly for our another experiment which focused on the DSBs and the biomarkers. So DSBs are DNA double strands, and they are complementary breaks in the phosphodiester backbone of the DNA and on the both strands of the DNA. So, and these DSBs lead to the complete segregation at the breaking point. So they are considered a common but very severe form of DNA damage, as they can promote genomic instability and the risk of cancer. And this is reflected, of course, in the elevated levels of DSB if we have the cancer or other things. So typical inducers of the DSB are the ionizing the radiation and certain cytotoxic agents, which are used in cancer therapy. So this opens a wide field for diagnostic and prognostic uses of DSBs in precision medicine. And for example, DSBs in radiological and pharmaceutical cancer management. And measuring the DSBs allows to quantify the extent of DNA damage during treatment and can indirectly indicate the DSB repair capacity as a proxy for the drug resistance. So such information could help to personalize the treatment and improve the patient outcomes by adapting drug or radiation doses to cellular effects. Physiologically, once a DSB has occurred, a cell will either perform an immediate repair or undergo apoptosis, or what's worse, instead of apoptosis, it can turn into the cancer cell. But yeah, the achieving the first one, so the repair, it requires a real complex repair process to compensate the lack of a complementary DNA template. And amongst the very first events that are the accumulation of the phosphorylation of the marker histones at the DNA breaking site. And therefore, the most widely used method for quantification of DSBs relies on the intercellular detection of fluorescence labeled antibodies, which just attach to the histones. So here you can see one of the images made by the automated software, where it's just the blue ones are the cells, the yellow circle are the detected cells boundaries by the automated devices, and these red dots are the foci that were found by the device. But in overall, we can see that not always this red. We had red dots on this foci, like example. I don't know if you see, but here, so it isn't really marked. Yeah. So to count this foci, we use the count data, and it's the count data just represents the number of occurrences of a signal as non-negative integer values, since this is one of the most common types of data, and the modeling of counting data is of primary interest in many areas, including the public health, medicine, and epidemiology. And it is generally assumed that such kind of a data just is fitted to the Poisson distribution, which is the most important part in this Poisson. So the another thing is that when you deal with the count data, you need to also deal with the overdispersion and zero inflation. So overdispersion is when the variance, it differs from the mean value, and zero inflation is when we have excessive numbers of zeros in our data set. And as for our for our experiments with the foci, we just use the 4 distributions. So it is Poisson when the variance is equal to the mean is equal to the variance, negative binomial, and B. So here we have the negative binomial is when we have the variance is much higher than the mean. Then we have zero inflated Poisson. So this is just the Poisson distribution with the excessive numbers of zero, and zero inflated negative binomial is the same as negative binomial, but with the excessive numbers of zeros. So in our equation, the lambda represents the mean. The R is the fraction of the counts that turn to zero. So it's mostly in the zero. So it only describes the zero inflated distributions. And we have the theta. So it's so it's the dispersion number. And the most important part is that if we do not correctly identify the zero inflation in the data sets, we can underestimate the real number of occurrences. So the model selection in our parameterization, NB and so negative binomial zero inflated negative binomial are treated as a mixture of Poisson and gamma distributions. And Poisson, zero inflated Poisson and negative binomial are nested into the zero inflated negative binomial, as it has all the parameters that could describe the previous, I mean this 3-1 distributions. But however, for example, zero inflated Poisson is not nested to the negative binomial, so that's why we needed to find such criterion to compare the fits, so it would describe both the nested and not nested models. So it was the Bayesian information criterion. I mean, so we choose this one, BEC. To fit the counts, we have used the 2 packages, PSCL and the mass. And to validate the countfitteR framework, we analyzed the empirical power with the simulation study and compared it with an existing 2-step procedure. And the empirical power is defined as the fraction of correctly identified distributions. So we have generated univariate data for these 4 distributions that we are working with, and then we generated also our data set consisted of 1,000 replicants and divided into 3 sample sizes and 3 possible means. For the zero inflated models distributions, we had the R from the range from 0.1 to 0.9, and in case of negative binomial zero inflated negative binomial distributions, we also set the parameter of dispersion as equal to mean, 2 times bigger than mean and half of the mean. And this is the result. So this is the result for the zip distribution. So we can see that countfitteR just overperforms the 2-step procedure, where the 2-step procedure also the black one is uncomputable. So the 2-step procedure couldn't compute all the data and distribute to the different distributions. The bigger problem for our countfitteR was the zero inflated negative binomial, where we can see that when we have a low number of low mean and low number of samples, the countfitteR works not good. So usually is outperformed by the two-step, but the higher the mean, the higher the sample size, we can see just clearly see that in most cases the countfitteR outperforms the two-step procedure. And we also check the Poisson and negative binomial distributions, but as you can see in this table, for the Poisson distribution, the two-step procedure couldn't compute almost 50% of the data which we inputted to it. So where the countfitteR just distributed, I mean, just fitted all the data to the proper distributions. And the problem was also a big problem with the negative binomial, where the two-step procedure only fitted the 69% of the data. Yeah, then we also, our experiment, the Focky quantification. So we wanted to see if these experiments, in vitro experiments, also follow these Poisson distributions, as it says that all the count data is following, most of the count data is following the Poisson distributions. So we just took a protocol for Focky quantification from our other experiment, and we have automatically counted the Focky numbers from the images with the cell prolifer and nuke detect, and this is the results. So we can clearly see that that the Poisson distribution was never the most frequent distribution. So that's why one of the main, for the countfitteR, we also developed a Shiny app for the GUI and our web server, so the other scientists could easily just input their data and just see, decide which distribution they can use. So in the web server, the main functionalities of it are the fitted models page, and they compare distributions. So the first one just represents the countfitteR framework. The count data is fitted to the distributions with the lower peak, and compare distributions allows in-depth exploration of the fitted models, so the user can investigate all the fits and their big values. So, but I want to also say that countfitteR isn't a decision-making system, but rather the decision support system, because the actual decision remains in the user's responsibility. So this panel, this compare distributions, just allows the researcher to determine whether the distribution is distribution suggested by the countfitteR is possible. So we also the important part of the web server is the report generation. So all inputs changed by the user are included in the report, so to ensure the reproducibility of the analysis. And this, to sum up everything, so although both overdispersion and disorientation are problematic during the analysis of counts data, it is very critical not to confuse these two phenomena. The increase of variance can result from the different factors, and the zero inflation is usually linked to the measuring devices and Focky counting algorithms, and both effects are unwelcome. So the two-step procedure seems to mix the zero-inflated Poisson and negative binomial, where the countfitteR can easily distinguish between between these distributions. And with our approach, we provide evidence that relying on this basic assumption that the Poisson distribution is not tenable. And a leading design principle of the countfitteR web server was to enhance the reproducibility by the providing advanced reporting functions, and the countfitteR is a powerful and easily accessible tool for the selection of the proper count distributing models are amongst these four distribution models that we have. The acknowledgements, funding, and the links for the packages. And thank you.
Okay, thank you, Jarek, for your talk. And let's go to the final speaker, Claudiusz Witczak from the Ministry of Health. We'll speak about differential equations or how we learn to stop worrying and tackle the coronavirus modeling crisis in Poland. Claudiusz, if you could share the screen and start your talk.
Everybody, my name is Claudius. I'm affiliated with the Ministry of Health of the Republic of Poland, and I'm going to guide you through the realm of coronavirus modeling, or how we do it in Poland. So I'll try to explain all the stuff in layman's terms so that no background knowledge is required. So let's delve into the topic. So SARS-CoV-2 is an infectious disease that is kind of different from most of them, in that it has an incubation period, which means there's a significant delay between the infection and the onset of symptoms. And this is basically why it has spread so well in the entire world. There's also a significant fraction of cases that are fully asymptomatic, which also helps spread it. It is highly contagious because the R0, which is the measure of how many people are infected by an average person, average SARS-CoV-2 infectee, is 3.3, which is much higher than the initial WHO estimate. And the virus is also quite deadly. It kills almost 0.7% of people that it infects. It is 7 times fold increase in mortality as opposed to, for example, influenza. And it's also very sneaky because the median incubation period is actually around 5 days, which is quite a lot. The risk profile is also very diverse and not entirely studied. But how do we study this? Well, there is a general consensus on complex systems. Most of the models that are being developed are compartmental, which means they divide the population into several categories. And the first model is the famous Kermack-McKendrick model, upon which all the other models are basically based. There are 2 approaches, deterministic and stochastic. That's simple. But let's delve into this SCIR model, which actually is developed for infectious diseases with incubation periods. So we have susceptibles, people who are not yet infected with the virus, but are not vulnerable to it. So they can be potentially infected, coming into contact with an infectious individual. We have exposed individuals, which have been infected, but they don't spread and don't yet know of the infection. There are people who are infectious. This is the compartment that actually spreads the disease. And people who are removed or recovered in some systems, but removed, which means that they are not studied anymore. We don't care what happens to them in this point. And the model is governed by some parameters like transmission rate of the virus, alpha parameter, which is the inverse of mean incubation period, and gamma, which is an inverse of mean infectious period. And I'll show you how how it is governed later on. So why was the model actually developed, our model? Well, simply to aid the decision-making process and help make informed decisions. In that it could, let me rephrase, we wanted to aid the decision-making process by simply forecasting the number of cases, the number of deaths, number of people being hospitalized at a given time, and also mechanically ventilated. And what was the principle of the model? Well, first of all, we wanted a time-efficient model, which is the model that we could run right after the arrival of new data without having to slouch all night, you know. So that was the main principle. We also wanted a model that is that allows for parallelization, so that we could further utilize, and you know, we can further utilize some maybe computationally expensive methods, but ones that allow us to save time, and also automate it fully and stuff like this, and protect it from erratic reporting patterns, so that when one source of data lags behind, we can impute it somehow in some sort of way. And seeing this, we settled for a deterministic model rather than a stochastic one, so that we can save time and we can make forecasting that is good enough for to simply study the situation, that study the current state of the pandemic. So the curious case of Poland, I tell this is how the slide is entitled, because it does not, this incidence curve does not look like any other curve in Western Europe or in Asia or in any other country, really. In that there is a very slight exponential growth, but then there's leveling out, and this plateau lasts for like 5 months almost, followed by an increase in number of cases. And then the last situation is kind of hard to judge, because there was a significant alteration to testing procedures or testing guidelines, really. So this incidence curve will not be accommodated by any simple and classical epidemiological model. So let's just delve into the notion of reproduction number, because this is very important and central to our model as well. So the reproduction number, basic reproduction number, is the average number of secondary cases that arise from a primary case in an entirely susceptible population. So we assume that everybody is vulnerable to the virus, everybody can be infected, and nobody is vaccinated. So there is a whole, the pool of people who are likely to be infected with the virus is the whole population. And this is known as a transmission potential measure. But there's also an effective reproduction number, which is a slightly different measure. And actually it says more about how the disease is controlled at a given time. So this is the average number of secondary cases that arise from a primary case at calendar time t. And this is basically the measure that we are interested in, because due to some controlling measures that are being enforced and being introduced by the government, for example, or that are actually the result of self-awareness of the people. So like self-isolation, quarantining, contact tracing, vaccination as well. This is not the case here as of yet, but it will be. And non-pharmaceutical interventions, which are the governmentally enforced laws, for example. And but regardless of methodology, if R is less than 1, the epidemic is said to be in decline, which in that it remains under control. But it is a very relative measure. For example, in India, the R is around 1, the effective R, with around 100,000 cases daily. So it is just a very relative measure, and it is good to know that. But if the basic reproduction number is around 1, that it means that this disease will probably not invade, in that you can nip it in the bud, basically, because it spreads, the spread is so slow and so low that it actually doesn't require the whole lot of control measures to actually not let it invade in the population. But if it's much higher, as it is the case with SARS-CoV-2, well, then control measures are indispensable. Well, and how do you estimate the RT? We utilize the so-called generation time, which is somehow related to the incubation period, in that generation time is the time between the onset of symptoms in the primary case and the onset of symptoms in the secondary case. And usually generation time is assumed to be Gaussian distributed or gamma log normal and Weibull distributed if the data is right truncated, because the incubation period is by design non-negative, However, the generation time, not really. It is not unlikely that the secondary case gets to see the symptoms first, earlier than the primary case, which is what makes this disease very hard to actually control. And you can also see that the incubation period is a little bit more long-tailed, but both the distributions are quite similar, and there's so much overlap that I decided to show them on the separate graphs. Both are, of course, positively skewed. We estimate the effective R on test-weighted 14-day moving average to actually deseasonalize the data, especially the weekly deseasonalization is very important. Also to not to actually prevent the estimates to be very bumpy, so that one outbreak could artificially inflate the value, the estimate value. And also we correct for the test positivity ratio. So if there are if the number of cases is high and the TPR is also high, the fraction of people that are the fraction of tests that are giving back positive results, then we also somehow punish the estimates by inflating them due to that. And we use the time-dependent MLD method as introduced by Wallinga in Tunis in 2004 after the SARS-CoV-1 outbreak. And here we simply look at the pulse of the observations rather than the entire network of possible infections, and simply sum over. We simply compute the relative likelihood of case I being infected by case J based on the difference in the onset of symptoms in both cases, and then we compute the reproduction numbers for each case J, by the summation of the relative likelihoods. So it is quite simple, really. And well, we extended the SEIR model by vital dynamics, which is kind of textbook approach. We use the demographics to actually enhance our forecasting. We use time varying parameters beta and gamma. Sometimes we do not use the gamma. We assume that gamma is fixed, but in most cases we use the time variation of those parameters. So we treat the SARS-CoV-2 incidence as a stochastic process, and then we identify some time intervals during which this process has significantly the mean of this process is significantly different, so that the intervals are as homogeneous in terms of mean, and in general the time intervals being as heterogeneous when you compare them in terms of the mean. And we fit different parameters in each of those time intervals. We introduce the disease-induced mortality parameter theta, also auxiliary compartments for medical resources usage. I'll tell you later while they are auxiliary, and you'll see for yourself. And confidence intervals, because the basic deterministic SEIR model does not actually accommodate that as in Efimov and Ushiro-Bida. So this is the flowchart of the model, which is quite simple, really. We have demographic live births and natural deaths. We have all those compartments that I said before, although there's no removed compartment that is being replaced with confirmed. We have the respirated and hospitalized compartments, and also dead compartment, which actually holds all the individuals that died because of the SARS-CoV-2, as opposed to the natural deaths that are deaths that happen from other causes. So this is the extended model ODEs for ODEs that for each voivodeship. So we have all those 7 compartments, and but rather than let you ponder over it, I'll try to skip to the parameter list. So we have those time varying parameters that I've already introduced: transmission rate, virus transmission rate, and mean infectious periods. And we have also non-time varying parameters. The first 4 are actually deterministic, but we do the optimization to find the values for the rest of the parameters that are here included here, such as hospitalization rate of the infectees, mechanical ventilation rate of the infectees, inverse of mean mechanical ventilation hospitalization periods, and also the induced mortality can be viewed as a case fatality ratio as well under some circumstances. So why don't we feed a simple national model to the data? Well, as you've seen, that there was a plateau of 4 to 5 months really, which actually prevents us from learning much from it. I mean, learning, for example, in terms of how does the number of infected people of people in the infectious compartment actually correspond to the resources usage, for example, and with the pandemic plateauing for five months, being totally leveled out, it is of no question. It is simply not possible to derive anything out of it. But if you look at the individual voivodeships, well, then the situation is quite different because, for example, in Lublin voivodeship, the pandemic seems to be creeping in all the time since the onset, really. In Lower Silesian voivodeship, we have seen a huge peak at the beginning, and now it is kind of it seems to have peaked, but at a slightly at a significantly lower amount of daily cases. In Mazovian voivodeship, it seems to have peaked thrice, and it seems to be growing, even skyrocketing, you might say. And in Silesian voivodeship, the pandemic seems kind of to be in decline, but it's hard to say. But it has already peaked twice and pretty significantly in comparison to other voivodeships. So how do we actually parameterize the model? How do we actually find the parameter values? We use the limited memory Broyden-Fletcher-Goldfarb-Shano method, LBFGSB, since it provides us with bound constraints for the parameters, so that we can, for example, restrict the gamma parameter, which is an inverse of mean infectious period, to be a value that is actually that is biologically viable, so that the mean infectious period is a viable quantity in days, for example. And we also want to constrain, for example, the beta parameter to be non-negative. And there are many constraints that are put to the parameters. So how do we do this? We do the calibration procedure is nested for each voivodeship. So for each plausible values of EK0 and IK0 or K0 or IK0, well, this is number of the initial exposed and infectious people. So you can view it as you can perceive it as imported cases, actually, but we find them as the multiplicity of the initial number of incidents in a given voivodeship. So it's not rocket science, really. So using those two for different values of these two parameters, we perform the optimization of beta and gamma parameters in time intervals using incidence and deaths data. And then we choose the tuple of those 4 parameters that actually minimizes the basic model fit to the data. The basic model, which means the model without the hospitalized and respirated compartment. And we use slightly modified RSS, weighted RSS to actually fit it. And in phase 2, we perform the optimization of those parameters, chi, rho, h, and r, that are responsible for the dynamics in medical resources compartments. And we use also the values estimated in phase 1. And then we choose the tuple that actually minimizes the model fit to data, to the observed data in the extended model. So in the full model that I've described earlier on. And then how do we actually perform the forecasting? So the central measure is the effective reproduction number. So for each voivodeship, we first project the effective reproduction number using some time series methods that tend to give the best results. And for example, hot winters with damped trends or semi-local linear trend methods. although the second one is slightly more computationally intensive, and it increases the runtime pretty significantly, pretty drastically. And then we assume that the latest dynamics from the latest time interval will be continued in terms of the mean infectious period. So we take it from the last time interval and keep it fixed, and then we assume that the virus transmission rate varies, and it is being scaled by the factor of effective reproduction number. And this formula is derived from the extended SAIR model. So at Tth forecast day, the virus transmission rate is estimated to be it amounts to this quantity. And then in phase 2, we actually parameterize the extended model with values that are obtained during the nested calibration procedure from the previous slide and the phase 1 forecasting, the first phase of forecasting. And then we initialize the extended model using the latest data on lab confirmed incidence, SARS-CoV-2 induced deaths, and resources usage. This is also the data that is being used to actually calibrate the model. So just to make it clear. And then we approximate the model that is continuous in nature at integer times using Runge-Kutta method, which actually bears little to no numerical error and is exorbitantly fast as well. And then we obtain the forecast for each compartment on the national level through summation over K voivodeships. And well, it is being done because this is the only way to actually maintain parallelization. If we were to introduce some kind of relationships between the voivodeships, then the parallelization is really hard to achieve, I believe. Although there might be some shortcuts that we did not actually take note of. So this is an exemplary short-term forecasting that was run on the latest data. Well, it is not the most compelling one, I have to say, because but in but one voivodeship, the effective reproduction number is below 1, and in all the rest, the effective reproduction number is actually significantly above 1, which means the epidemic is growing. So actually, there's an increase in both hospitalized cases, in respiratory cases, and the incidence and deaths are also seem to pick up some momentum. And well, it is good to ask the question, why R, right? Because this is the name of the conference. And well, when it comes to modeling infectious diseases, the simplest really the answer is really straightforward. On CRAN, there are like plenty of different and very well structured, well taken care of packages for epidemiology, and specifically modeling infectious diseases, such as R-Note for obviously for estimation of the reproduction numbers, EPI model, EPI model, EPI dynamics, one for the network models, one for the compartmental models. Both are absolutely great. This all is an absolutely brilliant package for solving ODEs for approximation of the solutions. And VCPT is the environmental package of dedicated to change point detection that we use to derive the time intervals of the parameter estimation. And also R is quite easy to parallelize the code that is actually already vectorized. It is very straightforward. So I guess that's another advantage of using it. But we have also a lot of prospects to actually enhance the model in some sort of ways. First of all, we think of introducing heterogeneity in the model, such as age and sex demographic structure, to help us make informed predictions. Also, as I stated before, the interactions between voivodeships are being considered as in a form of metapopulation model, which is kind of which has already been built, really, but due to the fact that it is not really easily parallelizable. Well, it is not being put to use as much. Then vaccination, which is imminent, and it really changes the dynamics of the pandemic in that it can introduce a lot of oscillations and drastically change the outlook. Also, the mobility data has been included, especially from the Google mobility reports. But due to the due to really patchy data that is being provided by Google, especially as of late, it has been detached from the model. And then there is the SARS-CoV-2 seasonality, which actually is something we have no idea about, because the other coronaviruses, 4 or 5 coronaviruses that are well studied, they seem to exhibit some kind of a seasonality, but it is not to such a great extent as, for example, influenza. So we have no idea whether this seasonality will take place in this case. So it's hard due to this. It is really hard to perform long-term forecasting for the SARS-CoV-2. And I guess that will be all. Thanks for the participation. Thanks for tuning in. If you have any questions, you can reach me here or ask them on YouTube or Slack. I'll try to answer them as quickly as possible. Yeah, that is it. Thank you for your attention.
Okay, Claudius, thank you for joining. And yeah, let's have the follow-up on Slack. So thank you all for joining, and see you on a keynote talk.